This is the opening plenary session on AI applications to forecasting and markets. And I think we'll have some great presentations and a lively discussion here. I'm going to keep it very simple, just introduce each speaker briefly, have 15 to 20 minutes to present. We'll save questions and discussion for the end. I hope to have 20 to 30 minutes where we can kick around ideas. Feel free to ask each other questions, as well as we'll take questions from the audience here going up at the microphones. So we're going to start out with Aaron Hill. Aaron is an assistant professor at University of Oklahoma, and he'll be introducing a lot of what we're going to be talking about here today. So please go ahead, Aaron.
Thanks, Mark. Let's make sure everybody can hear me. Yeah, hi. Good afternoon, everyone. Excited to be here for my first ESIG conference. As Mark alluded to, I'm an assistant professor in the School of Meteorology at OU, as well as a member of this National Science Foundation AI Institute called AI2ES, focused on applications of AI in weather and climate. I'm going to put on my professor hat a little bit today and actually start off with a question that I'm going to pose to you all, courtesy of my 5-year-old son. He drew a picture of this animal when I was putting this presentation together, and I decided I was going to make this part of our discussion. So in about 5 or 10 seconds, I'll ask you all to raise your hands if you think that this drawing is a bear, a horse, a dog, or a cat. So for those of you that think it's a bear, raise your hand. Okay, this is really interesting. How about B, a horse? All right, C, a dog. And D, a cat. Okay, great. It's super big range. Great. This was kind of the point here. So this is actually a dog, specifically a husky puppy, as I was told I had to emphasize. We are a UW family, so go Huskies. The point of this really was to kind of emphasize that you probably considered a variety of questions when you were looking at this image. Maybe you'd seen something like this before. Maybe you have small kids who have drawn something like this. Maybe you looked at it and said, oh, the proportions and the shape kind of look like a dog or a cat or a horse. There were something like legs in that image and maybe a tail. It had some ears and even some fur. So you likely considered a variety of questions, right? So the point being that we've been trained through experience, or maybe you can change that word to be data, to key in on features and patterns that allow us to identify animals in images, even if they're not drawn perfectly correct or like we might expect them to. So what does this really have to do with AI? Well, let's say I wanted you to look at 1 million images and tell me which animal was in each image. Do you think you could do that? Probably with enough time, with enough resources. You've been trained. You went through grade school where people told you this is a horse, this is a frog, this is a dog, right? Well, AI essentially replaces that process, right? It allows us to replace this finite human processing capability. Again, could you label all those images? Yes, with enough time. But computers can do it really, really fast. It has a lot of power and a lot of resources. And I've used this really simple example of labeling cats and dogs in images. But what if the images are radar? What if it's satellite? What if it's a numerical weather prediction model output, right? Humans can process that information, but computers can do it even more quickly. Okay, so let's talk about what AI really is at a fundamental level. It's a technique which enables machines or computers to mimic human behavior, okay? So in this example, human behavior is labeling an image. Maybe human behavior is deciding to go out to eat tonight. We can make a model that decides whether we're going to do that or not. It's really this broader picture of mimicking our brains and the processes that we go through to make decisions. Now, many of you have heard about machine learning, which is really a subset of AI. It's using statistical methods to enable computers or machines to really improve with experience. So we're all probably familiar with linear regressions. You have a Y and you have an X, and you give it 10 samples, and it maybe creates an okay linear regression. You give it 100 samples, 100,000 samples, that linear regression model gets a lot better, right? So that's an example of this kind of machine learning technique or pattern recognition. You've also likely heard of deep learning. I didn't like the definition in this graphic, so I just changed it real quick. More complex algorithms, okay, that enable richer insights into our complex data sets. We're all kind of in this science domain, energy, weather, etc. We have really complex information from the data sets that we deal with. So these techniques, machine learning and deep learning, really allow us to do pattern recognition, which is what forecasting is all about. So depending on what domain you're in, I'm in weather. I am probably one of the biggest weather geeks in here. I have chased tornadoes. I stare at the clouds a lot more than I probably wish to acknowledge. My domain specifically, I like to predict weather hazards. I like to predict tropical cyclones, tornadoes, hail, wind, and you can imagine some of the corollaries to energy. But depending on what domain you're in, you can ask these various questions and set up a problem that AI can solve, okay? You first have to figure out what do you want to predict, and you have to figure out what controls that prediction, and then you have to choose an F here, a function, the AI model of your choosing. It could be a regression model, could be decision trees, neural networks, generative adversarial networks, diffusion models, etc. And many of you may be familiar with those, many of you may not. But the point being that your domain allows you to answer these questions and set up the problem. So very simple, silly example is I have an Aaron is miserable index, which is a function of, is it hot outside? Is it humid? Are there mountains? Is it snowing? And I can create a decision tree that essentially determines whether I'm going to be miserable today. And in central Oklahoma, unfortunately, in the summer, that answer is often yes. These brief reprieves to the mountains help. But generally speaking, no matter what domain you're in, you can create a problem that AI can solve. So why weather? Well, I don't have to really motivate this too much. It's a crucial variable across a variety of industries and disciplines, right? Emergency management, agricultural commodity trading, energy markets, air travel. And we have lots and lots and lots of data that we have to parse through, okay? So we have data from weather balloons, from numerical weather prediction models, satellites, in situ measurements from airport stations. Even aircraft are taking measurements on their ascents and descents into airports. So all this information we have to process. Many of you use this information in your workflows. But when we're talking about forecasting weather hazards into the future, we often consider patterns, right? We consider patterns that have been in the past, analogs to what's going on currently, but we also consider the spatio-temporal evolution and the pattern that exists in the atmosphere. Humans are really good at recognizing these patterns. We've been trained to do so through meteorological curriculum, through experience, but computers can do it even better nowadays. Okay, we have improved computing over the last few decades, an exponential increase in computing power that really were enabling computers to identify these patterns and these objects and data that was traditionally done by humans alone, or other complex statistical algorithms. And nowadays, we have these data sets, these petabytes of data that can have really complex patterns as well. Satellite data, radar data, these images that characterize our atmospheric phenomenon that do have some intricate details. So AI is a really useful tool in this domain, processing observations, numerical weather prediction model output. We can bias correct forecasts, as was mentioned earlier today. We can generate new types of forecasts, which I'll talk about here in just a second. And all of this will really just help us meet client and end user needs. So I'm going to be talking about a little bit of my own work here in kind of high impact weather hazard prediction. Selfishly, this is kind of work that I've been doing over the last few years as kind of a demonstration of where AI can really advance our own predictive capabilities and understanding of severe weather hazards. So for those of you kind of less familiar, our current approaches for prediction of weather hazards include numerical weather prediction models. If we're interested in predicting tornadoes or hail or severe wind, which are really finite scale localized impact events, we typically have to use high resolution numerical weather prediction models. An example here on the left, this is a system known as WAFS, or the Warn-On Forecast System, 60-minute lead time for the probability of thunderstorms at a location. That's great. They're typically pretty skillful at those lead times, but what if we want to make a prediction a week ahead? There are practical and logistical limitations, both in terms of being able to run a model like that on a supercomputer, as well as predictability. There's error growth associated with these models that don't really allow us to go beyond about 3 days. So if we want to make predictions farther out in time, we have to take what's called an ingredients-based forecasting approach. So we know that severe storms and their attendant hazards require water vapor, instability, some mechanism to lift the air like a front. And so we can assess these ingredients over large spatial areas. So we can see that there's a jet stream in that lower right picture, and we have this general broad scale location of severe storm potential. But that's not really an explicit forecast. That's just saying these ingredients are here, you may see a storm, right? So the high resolution models don't offer what we need them to. They're not at the resolution necessary to actually resolve the hazards either. A tornado at largest scales, many of you may have heard of, like the El Reno tornado, it was maybe 2 miles wide. That's still not being resolved by these high resolution models. So what we do is we use proxies. There's an example using updraft helicity. It's a measure of rotation in thunderstorms, which are correlated to severe weather hazards, but that's still an implicit prediction. We can get that out of the model, but it's really just saying to us there are storms rotating. It doesn't necessarily say that there's a hazard there. So what do? Well, we can use AI because we have historical observations. We have events over the last 10 to 15 years where there was tornadoes and hail and wind. We also have historical records of environments around those observations. So AI is all about pattern recognition, right? So we can take these AI models and we can say, all of these past events, I want you to understand what is the spatial and temporal evolution of the atmosphere and how does that relate to these events? And we can actually produce these forecasts explicitly farther out in time. So this is an example of one of these forecasts. On the left there, where the colors are the probabilistic contours of excessive rainfall for a particular day, and the dots on the right panel there are where the actual events occurred. So we can get really good forecasts from these AI models. So I'm going to specifically talk about this prediction system that I've developed. We use an AI model called Random Forests, and essentially we ask a series of questions about the environment. What's the temperature like? What's the instability like? How much precipitable water is there around the atmosphere? So we can take a point like up here in the top right. We can look at the environment around that. And we ask these series of questions that get us at this answer of what's the probability of an event. And we construct forecasts to mimic operational outlooks. And when I say operational, I mean National Weather Service operational products that are produced by humans. The idea here that we can produce a first guess field of what the operational human-based forecast should look like. And the humans then can iterate on our AI product to better inform the public about where these hazards are. If you're more of a graphical interpreter, this is kind of a similar perspective. We have our inputs from the atmosphere, simulated rainfall, instability, pressure, etc. From our NWP model that goes out 8 to 15 days, we gather our predictors kind of in this 3-dimensional space or 2-dimensional space. It's a time series in 2 dimensions. So we can say how that atmosphere is evolving and how that relates to severe weather events. We have like 10 years of historical observations that we can train on, which is pretty robust in this space. And all that data feeds into a model. We throw it into a computer and it spits out real-time predictions. Okay, so what ends up happening is we beat the humans pretty regularly. And we're also extending our skill of these hazardous weather predictions way farther out than the current numerical weather prediction models are capable of. So this is a metric called Breyer skill score. Greater than 0 is good, less than 0 is bad. The green color is for our rainfall prediction system, and the purple blue color is for our tornado, hail, and wind model. All that being saying is we can extend these predictions pretty far out in time relative to what we were capable of even just a few years ago with just our dynamical systems alone. And this can have dramatic implications for emergency managers, National Weather Service offices, when they have to staff people. That's really kind of the primary purpose here, is informing them of when they need additional people on shift so that they can make decisions and better inform the public when severe weather is occurring. This hasn't been really talked about a lot as far as I'm aware in this space here. But one of the important aspects in weather forecasting and dealing with human forecasters is we have to be able to explain and interpret these machine learning models. And I talked to somebody earlier today that mentioned we just want good forecasts and that allows us to do our jobs better. But that trust is built up over time in the application and developing of these systems. one of the things that we're working on is actually interrogating these severe weather models to understand if they are learning the forecast principles humans use when making these similar outlooks. So humans use instability parameters, humans use wind shear parameters to determine if a storm is going to rotate. We're trying to understand if the models by default are learning these ingredients-based metrics. And in fact, they are. So an example here on the left, where a day 2 tornado forecast is heavily relying on wind shear, which helps to rotate thunderstorms, which is correlated to tornado prediction. Or that the instability peaks during the middle part of the day when it's the hottest, and that helps drive our hail forecasts. These types of explainability metrics are helping to build trust with our end users and forecasters, which is really a big ingredient to whether these systems become valuable and useful in operations. So just a quick summary. And I'll point out here, if you're interested in the graphics that we produce, I know this is a different audience than the normal people I present to, but if you ever want to look at our real-time graphics, we have a website where we produce all these forecasts. You can take a picture of the QR code, and I'm happy to discuss those with you later. But kind of in a big picture here, we're extending our capability in the weather sphere of forecasting high-impact weather hazards because we're using machine learning. This is kind of an advance that we've seen over the last few years, both using global prediction systems to drive local small-scale forecasts, but also improving the high-resolution model representations of severe convective weather as well. So in these kind of practical applications like weather, AI is really simply recognizing patterns in data. Can humans do this? Yes. Can computers do it faster and more efficient? Absolutely. And so we're able to relate environments, shapes of storms, other characteristics to these hazards occurring using this kind of rigorous training processes with AI and machine learning. So I can't spend enough time on this today, but I do want to emphasize that one of the really biggest impacts of kind of applying these AI predictions with forecasters is they don't immediately trust it. They really want time to be able to use the products. They want interpretability and explainability to boost their trust in it as well. And there's also aspects of trustworthiness and ethical responsibilities to build these systems with our data sets in mind and their own biases that are built into our algorithms. And I'll mention here quickly as well, there's kind of an overabundance of these data-driven methods to produce weather forecasts over the last few years. Models like GraphCast, Pengu Weather, now an AI model called AIFS. This is really the next wave, the next frontier of weather prediction models with AI, being able to simulate global prediction systems, being able to simulate the atmosphere in 3 dimensions with an AI model. This is relatively new, but really impactful. And one of the biggest areas is they're able to represent uncertainty in probabilistic forecasts, being able to generate 1,000-member forecasts, 1,000 representations in a matter of minutes, when we're just not able to do that with traditional dynamical systems. I just wanted to kind of throw that out there as another wave here, and I think that others may talk about that here on the panel as well. So with that, I'm happy to take any questions via email or after this session. Thanks.
Thank you, Aaron. And by the way, we will post PDF versions of the presentations within a couple of days here afterwards, so you can look at these slides again. I'm sure we'll have some questions when we get to the Q&A. Particularly interested in this interpretability, explainability type issue, which has always been a criticism of all of our modeling work, I think, is the black box is never trusted, even though it's smarter, right? So great. We're going to move right away now to Benjamin Toms. Ben is founder of Intersphere and looking at long-range energy forecasts.
Can you hear me? Yep. Cool. Yeah, thanks for the introduction. So my background is in something called sub-seasonal to seasonal forecasting. So I built these types of AI forecasts for longer range forecasts. So from 3 weeks out to a year. So I founded a company. I just transitioned to another company. So I'm mainly going to be talking about work that I did at Intersphere, not Climate Vision. So this is the team that I worked with to develop these AI forecasts. It was me. I have a background in atmospheric science. I have a PhD in that. I had somebody with no background atmospheric science. That's Jason, and then Jack is a blend. So like an interesting combination of skill sets. So when we developed our technology, when I started the company, I didn't want any private investment so that we could focus on the pure science and get that right without the pressure to sell right away. So this thing's cutting out. So we received all of our funding from the National Science Foundation. Everything was reviewed twice on the business side and on the science side. So that's the perspective that this work is coming from. So what I'm going to be getting to, this is kind of showing you the end. So you can create asset level, so wind farm and solar farm level forecasts out through the next year. And of course, there's some caveats there, like it's more accurate earlier on than it is later on. So this is showing a seasonal, so 3-month average wind power production anomaly forecast starting at 9 months in the future. So it's like 9 months through a year. And so, yeah, in this plot, like blue is showing where there's predicted to be less wind power produced and red is more. So when you make these AI models, you can go back and do back testing. So that's saying like if our AI model had issued a forecast, like on any of these dates from 1993 on, what would that forecast have been? And you can do that super cheaply. So Aaron talked about this a bit. AI weather models are now more accurate than the leading physics-based systems in the world. So this is an example output from Google called GenCast. So what these plots are showing is anywhere where there's blue, GenCast, the fully AI model, is beating the state-of-the-art physics-based system from ECMWF. So it's missing the labels here, but this goes out to 10 days at these tick marks. So you can see, except these are like high pressure levels, kind of in the stratosphere. These AI models are winning pretty much all the time. And then another cool study that just came out from the University of Washington showed that when you take these AI models and kind of perturb them with these physical patterns, so heating anomalies or something like that, you get very physical outputs that abide by physics, physical theory that we know. So they're actually learning the underlying physics of the Earth system in their own complex way. So this is an example of stirring up the atmosphere in the Western Pacific, and then Rossby waves emanate eastward from that. So if you're not familiar with what a Rossby wave is, that's like the high pressure and low pressure patterns that go over the United States. Okay, so now this is getting into a lot of the work that I did during my PhD and we did at our company. There are also a fair amount of other people and other companies working on this too. But the reason why people are so focused on this is this idea of sub-seasonal to seasonal forecasts. Those forecasts are very challenging to make, and it's known as this predictability desert. So this plot is from NOAA, and on the y-axis, it shows prediction skill. So if you have a color higher up there, you have more prediction skill. And on the x-axis, this is the forecast horizon. So it goes from hours to 2 weeks. That's what we're typically accustomed to. But then up to a few months, there's this lack or unknown amount of predictive skill. And then even beyond that, out to 12 months, you see that you do have some skill, but it's much lower. So a lot of people have been thinking about like, how do we create statistical models or AI-based models to be able to predict on these longer time scales? So the reason why it's so challenging to make these forecasts is that there are a lot of different atmospheric and oceanic patterns that go into influencing the weather a few weeks to a few months in the future. So this is another image from NOAA. So MJO convection, this is a big blob of rain over the tropics. And there's so it rains a lot in the tropics, and then these Rossby waves emanate outwards and impact weather in the United States. You also have what's called mesoscale SST ability. So that's these like little wobbles in sea surface temperature that happen over time scales of hours. And then you also have El Nino and La Nina, so ENSO. So yeah, totally different spatial and temporal scales, and your model needs to be able to integrate all of these together very effectively. So this is an approach that people typically take. This is, if you look at how people are making these models, this is generally what they do. They take a bunch of weather and climate data, most often it comes from reanalysis like ERA 5. They have a first step where they create this AI-based model for issuing these forecasts, similar to like GenCast from Google. And then they do some downscaling. So they have this coarse information, and then they make it very localized to things like wind and solar farms. So this is an example. It's kind of hard to see the dates at the top because they shift around. But these are backtests from an AI-based seasonal forecast system. So these are 3-month anomalies, 9 months into the future. You can think of this as a seasonal forecast that's issued for 9 to 12 months into the future. On the left is temperature, and on the right is wind speed. And so people with a background in pure weather and climate can pick out patterns that make a lot of sense in these images. But especially in temperature, you can see like these types of seasonal forecasts are more broad. Like you're not going to get a very localized anomaly over like one city that isn't also present over a broader region around it. And the reason for that is that the mechanisms that create these anomalies are also very large scale. So this is an old image from a pitch we did for our company. So this is our model, but that's not my intent here. So not a company pitch, but so a lot of people use statistical and machine learning based methods in the market right now. So part of evaluating these deep learning based AI forecast methods, which is what Aaron talked about, is can you beat those other methods, right? It's not just physics-based systems. The other statistical methods also have advantages. So from a fully AI-based, deep learning-based forecast model, the accuracy is on the left, where red, deeper red is better. And then if you only look at INSO, which is what a lot of people do, you might see on the news, it's going to be a La Nina, so it's going to be wetter or drier. People in energy markets also act on this type of information. So these AI-based models have much higher accuracy than those typical statistical methods. Another big advantage is, and I know people are talking a lot about probabilistic forecasts these days. So you can flexibly build your model to give you deterministic, which is a single value forecast like you would see on your phone, or probabilistic forecasts that capture the entire distribution of possible outcomes. So on the left, this is showing a single value forecast for temperature anomalies, right? So similar to what I showed before, you can see these large scale patterns evolving. And then in Houston, because weather derivatives markets care a lot about that, this is showing the, trying to get this to go again. So this is showing the probabilistic outcome for that one individual location that corresponds to the map on the left. So you can see this like evolving pattern of probabilities, and people can pick out like the most extreme cases of what would happen. So it's not just the average, it's like you can get the 10th percentile or the 90th percentile, things like that. Cool. So, this is getting to the final point. So we start with these weather and climate forecast systems, and they're built specifically to predict just weather and climate patterns like temperature, wind, rainfall, right? But especially in energy markets, what people really care about is power production and demand. So Aaron also mentioned this. You can have a workflow where you create these weather and climate forecast systems and then build secondary machine learning models, tune them to specific, targets. So it could be power production. So this is an example, try to get this going again, of wind power production anomalies in one of these fully AI-based forecast systems. Again, it's this backtesting idea. If you had your model forecast in all these dates, what would the forecast have been? So you can see that like it's capturing these, rapidly evolving patterns in, higher than normal power production or reduced power production. And this can be done for every single wind farm on Earth, which is what this is showing here. So yeah, then, I already talked about this a little bit, but backing up, you start with what's on the left and you can get to what's on the right. So you start with this purely weather and climate-based forecast system. People don't really act on that information. They want to act on power production. So, that's the ultimate end goal of these types of models that people are building. I move fast. So Aaron also talked about this. So this is based on work from my PhD. So when we were trying to sell these forecasts at Intersphere, a lot of people were saying like, you know, your AI model might be more accurate, but it's just cooking up that answer using something we can't understand. Or you're gaming the statistics, right? Like you're overtraining on what you're validating on. You know, there's all these questions and distrust. So you actually can go through one of these really sophisticated deep learning models and evaluate the exact patterns for every single forecast it's making that it's using. So animation's fun. So what this is showing is if you're predicting temperature anomalies at this blue dot, it's like somewhere in Missouri, which patterns in the surface pressure field are being used to make that prediction. And so looking at this animation, what's really cool is, you know, weather and climate scientists can immediately pick out patterns that we know are used to make forecasts in a statistical sense or with underlying theory. So like this region here is the North Pacific Oscillation. And then this region here, or the North Atlantic, is the North Atlantic Oscillation. So it might seem counterintuitive, but if you get pressure patterns to the east of like Missouri, it changes the wind flow over the United States. And so that can change like wind speed, temperature, precipitation. So yeah, when you see a plot like this, you know, weather and climate scientists say, hey, it's actually something that we understand. Yeah, so questions, wait till the end, or you can contact me directly. You don't need to just contact me for my company stuff. If you want to talk about this and understand it better, I'd be more than happy to do a video call or email, whatever works for you. Thanks.
Fascinating. Thank you, Ben. Thank you. All right. Next, we're going to move to Eric Grimit, Technology Manager, Applied Meteorology for Vaisala. Eric, welcome back. Many times here.
Thanks, Mark. Can everyone hear me okay? Great. Yeah, it is good to be back. It's been a few years since I've spoke at this event, but I've been involved in renewable energy for almost 20 years now. So long experience. I work for Vaisala. We're a global leader in weather and environmental measurements. And in our X-Weather division, at which I lead our North American science team, and we bundle our hardware and software solutions together and provide data as a service. So in terms of renewable energy, we're a forecast services provider. We provide wind and solar energy forecasts to support the energy transition. Today, I'm going to talk about our efforts recently to improve solar nowcasts and do kind of a review of what is the state of the art in cloud nowcasting using AI, and specifically that deep learning category, so deep neural networks that are a subset of full AI, as Aaron described. To illustrate this, it's useful to look at an example solar project just from one day. This is a utility scale PV project in the Southeast USA with data in blue shown every few minutes. And we have a baseline forecast that only considers the recent observations from the site, as well as a collection of numerical weather prediction forecasts. Those are the only two ingredients to this forecast. And, you know, while it certainly has some good qualities, the day starts off mostly cloudy. Our forecasts assume that it's going to stay mostly cloudy and not clear up as much as it does. And so the power exceeds the forecast by a good amount during the mid-morning period. And then later in the day, as it sees that, well, it's actually quite a bit sunnier than predicted, then it's trying to, you know, go back toward that more mostly cloudy conditions later in the day. So, you know, this is kind of the baseline forecast of where you might start, something relatively easy to produce. It has machine learning in it, but it doesn't consider anything outside of those two data sources. And really, this is where additional ingredients could be helpful. Some spatial awareness, looking at that pattern recognition around the site that you might be forecasting is helpful. And here's another example from a utility scale site in the Northwest USA as an example where, the numeric weather prediction resolved cloudiness doesn't catch some of the things that are happening on the smaller scales. And the past observations can only partly help you in this case. So in this example, the prevailing flow near this site in Montana is from the southwest, and you can see, if you look kind of closely from the back, a couple cloud bands that move through, causing 2 consecutive down ramps with an intermediate up ramp in between. And really, even though some of our numeric weather prediction models assimilate the satellite data into their cloud analysis and do the best it can with progressing that, no direct satellite ingredient is included in this particular forecast, but clearly one is needed. When I talk about nowcasting, I'm really looking at the first 0 to 3 hours of predictions. This is the AMS official definition of nowcasting. And here I'm looking at wider spatial areas. So there's also a whole rich field around using sky cameras in the very short term, say 15 to 30 minutes ahead at a local site, but that you lose sort of the spatial scale of being able to do something, say, continental wide, since we don't have a large installation of those kinds of devices around the country or really any country or continent at this point. And so I'll be focusing on this time period from sort of 0 to 3 hours ahead and taking a look at what is the state of the art, what's been done in the past in this area. If you go way back into last century, it really started off with extrapolation techniques. So you might first create a binary cloud mask. So binary being where is it cloudy, where is it not, by segmenting a satellite image into cloudy and non-cloudy pixels. And then assign or compute estimates of the motion, cloud motion vectors from successive satellite images, and then use those estimates to advect or extrapolate that cloud mask forward in time using those cloud motion vectors. And this kind of technique is actually the basis for the EU METSAT's official kinematic extrapolation product known as EXIM. And here's an example from one of our products as well, just using a simple interpolation or extrapolation technique. The big problem with this is that you have, for each pixel, clouds at different levels that can be impacted by different wind speeds and wind directions, and you have to assign a vector for each pixel. A more complicated method for identifying the pattern of apparent motion of objects and edges is optical flow-based techniques. So this is basically a gradient-based estimation of cloud motion vectors computed from consecutive images. So you take the difference between the cloud field at T1 and T2 and compute an energy or motion field that then you apply to warp the latest forecast image. This can, of course, only predict the movement of the features found in the current image, not any longer-term evolutions. So physical processes such as orographic lift over mountain ranges, convergence, frontogenesis, and thunderstorm convective initiation are all not well captured by a technique like this. But if you look at kind of the basis of it, it's a pretty solid starting point. Dr. Sue Haupt here led a really big project at NCAR several years ago that's been reported on in past workshops at this meeting. And her team leveraged several observation nowcasting technologies, each with its own sweet spot. And this included 2 components called Ciracast and Madcast that take these kind of satellite-based cloud advection approaches using different techniques. And this study found that all of these technologies had their sweet spot, had their areas where they perform well, and by blending them together, produced the best optimal solution across all different conditions. They measured this in terms of improvement over smart persistence, which is a good baseline to score yourself against. Essentially means that the cloudiness or the clearness index that is happening right now will continue. And so your improvement over that is a basis of how much better the forecast is than a no information forecast. And as a quick summary metric, overall lead times less than 6 hours in the study, the improvement of these techniques range from about 36 to 56% under all sky conditions for each component. There are, of course, more details, and I encourage you, if you're not familiar with this work, to read the summary paper in the Bulletin of AMS or the longer report for more details. I should note also, though, that this optical flow technique was not a baseline of comparison in this particular study for the cloud-based advection techniques. So what's been happening lately, in the last 5 or so years, applying deep learning to this problem? A number of studies have actually tested this now for the purposes of better solar energy forecasting. And it started first with taking the most common deep learning model architectures. Some of you may know, I'll kind of breeze through this, a convolutional neural network or an encoder decoder or UNet type architecture were applied to this problem first. I'm not going to review all the different papers that have studied this, but just collect some highlights of interest here. One paper by Meteorology France's AI lab by Batomier looked at cloud cover nowcasting with deep learning using Europe's MET11 cloud cover analysis. And there they showed that all of the selected models improved over persistence, and that a UNet architecture surpassed their NWP model known as Ahlstrom, as well as this XIM satellite extrapolation methodology. A paper the next year studied over Romania that they called DeepSat. It was a deep learning model for prediction of satellite images for nowcasting. Also showed promise for a CNN-like architecture. In fact, they use a specialized version of that. And the interesting thing in this study was that they actually showed that a multimodal or prediction of 5 different channels at once was useful. Later approaches in the last couple of years have now begun testing model architectures which combine encoders with recurrent units, which better capture the time series evolution together with these spatial covariances, these patterns that you see that are made in our atmosphere with clouds. And the motivation on this really increased because these techniques were in parallel being shown to significantly outperform both optical flow and state-of-the-art numerical weather prediction, especially in precipitation nowcasting. 2 of these techniques, one known published as SunCast, it was a solar irradiance nowcasting method by some folks at Cal Berkeley, looked at GOES 16 imagery, and in fact, the level 2 product where they estimate downward solar radiation directly and predict that the future images of that project, or of that product rather, using a convolutional long short-term memory network, or CONV-LSTM for short. It outperformed the high-resolution rapid refresh numerical weather prediction model by 13% in an RMSE, or root mean squared error sense, but only for the daytime. They did restrict their study to the daytime hours between 10 a.m. and 3 p.m. And so that still leaves open the question, well, what about those early hours of the day, right? That night to day transition is a key place where optical flow methods can't work because you can't see the clouds, especially in the visible channel at least. A 4th study was done by some folks at the University of Amsterdam, published in 2022. And they used a structure preserving convolutional gated recurrent units structure for the temporal, to model the temporal evolution, as well as a structure preserving loss function. So a lot of these studies noted, with convolutional neural networks and some of these earlier architectures, that the cloud field forecast would get spatially smooth as you went out and further in forecast lead time. And this was one way to try to combat that and preserve structure in the predicted images. This technique was shown to beat optical flow in a mean absolute error sense by 9 to 12% at 1 to 3 hour leads. And in turn, those optical flow methods beat persistence at predicting satellite images over these various European areas by 11 to 17%. So in aggregate, about a 20 to 25% improvement. So we'd like to introduce our version of this, building on those kind of 4 key studies, X-Weather Cloudcast, as an example of a specialist deep neural network that we've trained to do satellite-based cloud nowcasting in our X-Weather division, not only for the purposes of solar forecasting, but also all weather forecasting. Our approach really wanted to build on that multimodality. So we wanted to use multiple channels of the satellite data, both as inputs and targets. So utilize the visible and infrared radiances together because they benefit the other and assist, especially with the night to daytime transition. We wanted to make sure we stayed in this image to image sequence paradigm. So using a stack of recent images to predict the next few images. And in this work, we're not going to do any remapping or interpolation. Of course, the point of view of the satellite has various look angles when you're further away from the nadir. And here we're not accounting for that. We're just retaining the native projection and resolution of the source images. Our timing requirements were every 5 minutes. With the Western imbalance market and other developing needs, we see that rapid updates are both now needed and possible. And so we wanted to create a new forecast every 5 minutes based on the latest scan over the limited area scan windows over the USA and Europe. And so we targeted a 4 to 5 minute time as the maximum inference time for these forecasts, trying to keep the deep learning models as light as possible. And we wanted to create forecasts for the next 3 hours to cover the needs of intra-hour solar power nowcasting. So here's an example of what our training data looked like for GOES 16. We trained over the year 2022, scattered in a 4-2-2 split, train, validation, and test over the year, but not using all days. And here we're looking at the CONUS window, so every 5 minutes over the GOES East area. And our inputs and outputs, so the primary inputs, the things we both take in and predict, are 3 different level 1 channels. One, the visible spectrum, channel 7, or 2, sorry, near infrared is channel 7, infrared is channel 14, and then also level 2 product known as the cloud mask itself, so that 1-0 binary cloud mask. And we also provide some auxiliary inputs to the neural network that are not also predicted, which is the elevation, the solar zenith and azimuth angles, as well as the forecast lead time we're targeting every 5 minutes between the first interval out to 3 hours. Just wanted to show you a little bit about our first attempts. We looked at a couple different candidate model architectures. One similar to what's known as Google's MetNet, which is an encoder convolutional LSTM attention combination, if you can give it a quick name. And basically, this is a leading option from the recent precipitation nowcasting advancements that Google's shown performance superior to both persistence and the high resolution rapid refresh. Although we did modify it pretty substantially to reduce the number of trainable parameters. You can see, though, on the right in our movie that each target area only produced a smooth field near the mean value, so it isn't very detailed or really all that realistic. And the scene background, the areas that are not actually cloud covered, seem to confuse this particular algorithm further. Inspired by the work at the University of Amsterdam with the convolutional gated recurrent units technique, we applied a similar approach, but using a more efficient image transformer that performs well in the classification tasks known as a COAT. And so we combined those 2 architectures together, calling it a COAT GRU. This is basically an off-the-shelf approach that we could apply quickly that had a smaller number of trainable parameters, so not so heavy on the training and inference time as well. And the early results, as you could see here, immediately showed more realism, so we went in that direction. Here's some details on our model architecture itself. I won't take you through that here. If you're interested, it's in the slides. Our baseline comparison methods are basically that, hey, this extra effort and computational cost of training and deploying a deep neural network should really be justified by significantly outperforming baselines. And the most strong baselines we could get are all from this optical flow techniques. So we actually compared ourselves against 2 of them, this RAFT method, which comes from computer vision, and then a well-known one in the meteorology world that comes from radar and precipitation forecasting known as SPROG, or spectral prognosis. And just to get you a sense for the evolution of our results, at least for the channel 14 infrared part of the spectrum, over time, the orange curve is our raft optical flow baseline, and the blue curve is our neural net, and lower here is better. This is the loss, which is in our case is something like the mean absolute error. And you can see that as we iterated and improved aspects of the architecture and feature set, the loss scores came down. And by the end, you see our final model results evaluated here on a CONUS or continental US-wide basis as pretty good. So we see about, if I could pick out one lead time in particular, at 30-minute lead time, we see a 24% improvement over the best optical flow baseline. Here I'm showing both RAFT and SPROG. You can see SPROG actually does a bit better at later lead times than the computer vision technique. But for the visible spectrum, we really see the benefits. And we think that most of these benefits are coming especially in the early, or these extra benefits are coming in the early hours of the day with that night to daytime transition, where we see 50% improvements over optical flow in channel 2. You do see the crossover point is near about 10 minutes or so. So at the first few frames, optical flow is quite good. You know, it's almost like a copy paste type operation at those timescales, but this can still be an area where something smaller scale like a sky camera can provide benefits, but on the whole, this looks pretty good to us. There are smaller percentage improvements at short lead times and larger scale at longer lead times. We also evaluated our results by climate region. Here we're using EPRI's solar forecast arbiter climate zones definition to stratify the results, and we see up to a 40% or 41% improvement over optical flow in the Southwest USA and climate region 3, and about 20 to 30% elsewhere. And these are what the curves look like. So climate region 3 is the one in the lower panel, second from the left, and the others are scattered around. You see they asymptote to about 20 or 30% by about 30-minute lead times. And we get 40% or more in climate region 3. It's just an example of what this actually looks like compared to optical flow in a movie sense. So SPROG is on the left and our Cloudcast is on the right. From an example case, you can see that optical flow, of course, preserves some structure, but maybe unrealistically so. While our Cloudcast does show limited performance, it's smoothing out the fields in longer timeframes, which is a common problem for non-generative AI models or data-driven nowcasting models. Here's an example from Meteosat 10 over Europe with the visible spectrum for a different case, just really illustrating that nighttime to day transition. And even though optical flow preserves the cloud structure, it can't handle the changing solar angles. So these techniques are really here and showing promise. Our current progress is that we're using modern machine learning operations practices to deploy this into our operational environment to improve both solar forecasts for customers and also other weather forecasts. And we're taking the same approach that the NCAR Sun Forecast program described and incorporating this as a new input data source and blending it with our other valuable data input sources. So this isn't the only thing driving our solar power forecast. And Pascal will talk more about that in session 3B tomorrow. And we also plan to extend this to other geostationary satellites as needed. Future improvements. Well, these developments come really fast, a mile a minute. Deep learning continues to rapidly evolve with just disruptive new ideas coming to all of the earth sciences and probably the power systems field as well every few months or even weeks. There are new classes of generative AI models that have shown promise in things like natural languages and new training methods that are being evaluated by many researchers, both in the public and private sectors. In particular, you've probably heard a lot about generative adversarial networks and diffusion models because they've been so popular lately. But the really question is, will they yield another step change in accuracy, and are they worth it in terms of computational costs? So, maybe we'll get those answers soon. But I know we'll be there to continue to monitor, collaborate with others in this sector, and innovate to bring the best technologies to bear for renewable energy forecasting. So thank you very much.
Thank you, Eric. Very good. We're going to move right ahead now to Alan Smith. Alan is a senior fellow at NextEra Analytics.
Thanks, Mark. I actually have a title change. I'm Senior Director of Energy Management now at NextEra Analytics, and going to shift gears a little bit and talk about the way that we use AI to create market offers. And it's a great segue from Eric's presentation on forecasting because it's an important part of our market offer process. So at NextEra Analytics, we focus on renewable energy primarily, but also other types of energy production across the US and Canada. We focus on data and data analytics across 30 gigawatts of renewables operating in the market. At NextEra Analytics, our product that focuses on energy management is called NextEra 360. And within that application, we focus on both the design and operation of our units. And it may be operation of units that are dispatching outside of an established market or within an ISO where market offers play an important role in the facility operation. In all these applications, it's a data-first approach. Data plays a role in the way we both optimize the generation and also make sure that our facilities are operating optimally. I wanted to kick things off with this word cloud from a couple of different perspectives. This is generated from the California ISO Real-Time Market Operations Business Practice Manual. And for market offers, where we start is the tariff and the real-time clearing engine, day-ahead market, and what the rules are of engagement on the way you participate in the market. And there's not too many surprises here if you look at it, right? It's energy, capacity, ancillaries, scheduling, and operating and dispatch in the market. And so it's very simple, right? This word cloud was generated from the 300+ page document, and that's part of over 1,000 pages related to the tariff and the business practice manual for the ISO. Of course, we don't operate in a single market, so let's do this and add PJM. And it's interesting that the result's very similar. In PJM, it's a very similar market design. Maybe reserve is added, maybe a little bit of different aspects of real-time ancillaries. We see regulations show up as well. Very similar situation though. And we can do that at ERCOT also. And with ERCOT, there's a few more parameters we have to consider. The real-time market's more of a focus. There's 15-minute from California shows up, but also load. And Queasy is the market participant definition in ERCOT. Within all these, right, the basic premise on market offers are the same. Each of these designs are different. I didn't add SPP and MISO and New York ISO and the ISOs in Canada or ISO New England, right? But with each of those additions, there'd be yet another set of terms because there's no standard across all these different markets. And the devil's, of course, in the details, because even though many of these terms are very similar, the offer processes and the dynamics are different. We start with these requirements, though. And what we do, we need to use AI and the different forecast processes to create a point of view for the future. And that starts with the weather, the solar forecasts that we've been talking about. as well as market demand and reserve and peak requirements from a load perspective. Market imports for many of the markets are critical as well. And then for both day ahead and real-time operations, both generation and transmission outages can be critical also. So we have different ways to create the forecast for many of these parameters, which then factor into our point of view for a resource forecast. At the end of the day, we're making offers for each resource that we operate in a market, whether it's a NextEra asset or a third-party customer asset. And as part of those forecasts, we need to create that point of view for day ahead and real-time operation and market participation. There's typically multiple products that have to be considered, whether or not we want to participate in energy only, participate in different types of ancillary, or just focus on one or the other or a combination of those. In many markets, those products are co-optimized, and in some they aren't. The availability of the resource is important. Do we assume the resource will be fully available, or is there some sort of probability that there may be an issue with the unit? And in some markets, the day-ahead obligation is binding, and so if we do think, or if there is a probability of an issue related to operation, that's part of the equation. Specific to storage, we also have to think about state of charge estimation. That's part of the process for both day-ahead and real-time operations, because different markets focus on that in different ways. And when it comes to state of charge, if you participate in ancillary markets, you have to determine how much you will be dispatched for that ancillary product. Most of those products clear on a capacity basis, and then depending on the ISO's needs within the dispatch interval, you may or may not get dispatched for reg down. So your SOC may or may not change. So all those factors are important, and we need to have a point of view at the resource level. As was mentioned earlier on the solar forecasting on 5 and up to 180-minute forecast, that time horizon's very important also in a consideration, because there's a window that has to be considered. I call it the time horizon from bid close to the end of the operating interval. And in different markets, it's different. In California, there's a 75-minute window from bid close to the beginning of the operating hour, and that bid's binding for 60 minutes. So in that market, in real time, it's a 135-minute interval that we're trying to predict the future on. In other markets like ERCOT, it's more of a 7.5 to 10-minute interval. You have the opportunity to update your offer every 5 minutes. And so there's very different time horizons and considerations that are part of the process. And it creates both opportunities and challenges. When it comes to the day ahead market, it's bow day plus next day. And so that's more of a 36-hour point of view to predict and focus on. So we use different techniques and also multiple options for many of these forecasts to create the best point of view for inputs for these key assumptions. And using those, we can create strategies. And through primarily machine learning, we produce strategies that meet all the offer requirements. It's a ticket to the dance to meet all the offer requirements in an ISO. And then we focus on optimizing revenue and while meeting risk objectives. And when doing this, in addition to all the forecast that we just talked about, there's also additional resource configuration constraints that have to be considered. A few of the different constraints that may apply is a shared point of interconnection. In California, many projects, storage projects, are co-located with renewables. oftentimes solar. And so the variability in that solar output is an input to our offer process, not only for the solar site, but also for the storage site. And so those forecasts in the near term are very important to predict what we believe will occur with the storage due to the shared POI. In other cases, the energy storage charging source may also be a variable that has to be considered. In some cases, storage sites may charge only from renewables, so it's yet another variable. If the cloudiness is severe in the morning time, we may not have the charging energy that we expect to have. And so we have to constantly consider that charging source as we move through the day. And finally, work is never complete. In the market, it's a 24/7 operation, as we all know. And once we have a strategy, it's really something that's constantly updated with new data as it comes in to support real-time operations. The offer update process runs either every hour, or in the case of ERCOT that I mentioned, every 5 minutes. We have new data coming in based on the past operation of the unit, new market conditions. All those are being evaluated and create a new point of view for the upcoming period, as well as typically the balance of the day. And that storage evaluation is repeated again and again as well, because we may have a day ahead obligation or a real-time obligation that has to be met for an interval. So that continuous process is key to our product and strategy as well, to make sure that it's reliable, the update and the data flow is consistent, and we're constantly making those updates. So this process is, in my view, it's just critical to support the efficient resource optimization, but also the market operation. And certainly it's a partnership among the market participants, the resources, and the different ISOs to utilize AI in a way to support forecasts that optimize offer strategies to support the reliable operation of the ISOs. And then also there's one constant in life, right? And it's change. That goes back to Greek philosopher nearly 4,000 years ago. And we get new insights, new strategies that have to be evaluated constantly. The word cloud that we started with, it changes almost not every day, but once a month, right? As new rules come out, changes occur in the markets, changes occur with the offer process. And then also the energy market is dynamic and conditions change at each resource. And so those changes get factored into our strategy as well. So appreciate your attention and look forward to your questions.
Thank you, Alan. The interface of these forecasts with the markets and a lot of complexity. As you say, it's changing. Every market's different. Tens of thousands of pages of rules, and they're constantly evolving and thinking they can, well, maybe I want to control the state of charge of every battery myself, and change rules on stuff. Yeah. So we'll see. Next and final speaker for our session here before we get into our discussion is David Larson, Technical Leader of Grid Ops and Planning for EPRI.
Great, thanks, Mark. So my talk's gonna be a little bit different. We've had plenty of talks on very specific AI stuff. I'm gonna take a little bit of a step back and talk about some trends and challenges we're seeing and share some results from some evaluations that we've done. I won't be able to get into everything that I would like given the time, but I'm hopefully gonna hit some key points that people will appreciate. So when we talk about particularly forecasting and system operations and the use of AI and things like that, though this applies in other places, we're seeing some general trends, and some people are further along with these than others. Some of these items are already standard, others they're starting to think about it, of going from deterministic to probabilistic forecasts. Thinking about, we just use one single forecast model for our solar or for our wind or for our load, and others are thinking, why not have multiple models, maybe from multiple vendors, and combining those in some way. There's things about, when you think forecasting operations, you're typically thinking transmission. It's coming up more and more on the distribution side, and questions there about either because of necessity or what are the benefits of adopting some of these technologies and how we operate. Of course, you're thinking about, as you adopt these different systems, that hourly is just no longer sufficient, depending on the forecast horizon, that you're missing out on certain items and you need to go sub-hourly. And then there's just more items that you may be forecasting. Maybe right now you've got your head around, hey, load, solar, wind, I can do that. Now someone's saying you got to forecast a battery or hybrids or DRs or whatever. How do you even start that? There's no physical relationship with those. You need data and lots of different challenges. So I think across this audience, folks are seeing different levels of this. I'll say there's 4 challenges. There are lots of challenges, to be honest. I'm going to mention 4 that I think are important and talk a little bit about some results we've done specifically regarding number 4, but I think a lot of these come up in different places. So on integrating probabilistic forecasts, I think that's where a lot of folks are at. It's, you can go out and get probabilistic forecasts or make your own. I think people are more comfortable with that at this point. The question is, what do you do with that? Most processes are set up for deterministic, and then there's all these different steps of like, sure, in theory I could do this, but I can't give this probabilistic forecast to my operators in the control room. They'll laugh me out of the room. Or it's like, my system isn't set up to compute this. I have to run this in a certain amount of time. How do I modify things? And so I know there's lots of great work going on, including that ESIG probabilistic forecasting user group, and it's great sort of talking through these shared challenges. Another big one that is not exactly new, but it's coming up more and more, is just you're having a lot of these DR resources, and more particularly things that are affecting load, but you don't have that telemetry for them. Maybe because it's not required, maybe it's just because that data doesn't exist, or it exists, but you don't have access to it, and thinking of what can you do there, because they're not gonna go away, so you gotta do something. And it could just be right now you're dealing with behind the meter solar, but now you're thinking about these other resources coming online and what are the challenges there. Another big one that I think Winter Storm Elliott really brought to everyone's attention again is about tail events. You maybe want to categorize extreme events, but I think the general point here is that things that haven't occurred that regularly in the historical record, what do you do with that? Can you do anything? If it's a black swan event, you're kind of out of luck. But are there things you can maybe think about or position yourself? Maybe you can never forecast this precisely, but maybe you can do things to prepare yourself with the forecast and understand the uncertainty of, we don't know what's going to happen tomorrow, but we know it's highly uncertain. And that maybe gives us better decision-making support. And a last one that I know we echoed quite a bit in this morning's tutorial on data is just having more data and validation. Particularly for AI methods, you see that in other fields where people talk about this frictionless reproducibility. Someone publishes a new method, they put up on archive, code is on GitHub. A week later, someone's got a better version. And it's these incremental updates, and some people have sort of argued that that's the reason that certain fields have advanced so quickly. Of course, lots of different challenges in the energy space about making data and validation open, but I think there's some potential there that we all need to continue to discuss. I think that was one of the topics from last year's workshop about data, and I think it's just going to continue to be an item. So I'm going to highlight a couple of results that I think will be interest to folks, and then can always talk about this in more detail later. One is about a solar power forecast trial we did. And so this was one that we partnered with a utility. These were deterministic power forecasts. This was kind of a more than 2 birds, 1 stone. It was multiple things of, hey, EPRI is always interested in research. This utility was interested in seeing what's kind of the state of the art and evaluate a few things and doing it in a way that was going to be insightful for them. And so this, we were able to partner with them. We had 4 utility scale power plants that are operational. They varied in size. They had roughly all the same DC to AC ratios, but single and fixed tracking. It was meant to be sort of a representative set of their overall fleet. We had multiple forecast schedules, or I'm calling schedules of like, we had day ahead, we had down to real time that matched what the utility used in operations. And so this was all set up to be as realistic as possible. And we were fortunately able to recruit 9 commercial providers of forecasters to do this competition or this trial. And we had 12 weeks where every day they were submitting forecasts and being evaluated and going through. So this, I think, is one of the most realistic evaluations that has been done. A key part of this was that we used the forecast arbiter, or maybe folks know it as the solar forecast arbiter. So this was previously a DOE project, and then EPRI's taking over management after being involved before. But this really enabled us to set this up where each of the participants was anonymized. They could see results in terms of where they ranked compared to others, but they didn't see each other's data. So everyone was cool with that. The utility could see results, but then it was set up in a way that it wasn't possible for them to be biased because they didn't know who was who. So they had no idea if this was a startup that was brand new and they were just beating everyone, or is this an established player that maybe it was their existing vendor. So this was great. I'll just mention a couple of quick results. I don't have time to go over everything. As we expected, we saw some variation between the different forecast providers, and there was some variation by horizon. The reference forecast there is actually based on the HER model. And a little side note is the utility was so happy with the reference model and the control that they had of that, of just using the HER model and ingesting it, that my understanding is they've actually now put that into operations as an additional forecast to look at. So that they were able to see like, hey, this is how it performs. And they saw on certain days, yeah, maybe on average the error was a little bit worse, but they're like, wow, that actually captured that event. And this is already a model that's running. So we have our commercial vendors, they're great, but they felt comfortable having an additional forecast. So in this, you also see some variation between, I'm just putting here sort of roughly of like, 2 different forecasters to highlight them. Lower values here is better, but some interesting things there. Another one that we saw, and this is now looking at weekly averages of these scores, is that the gray lines are all the different forecasters, and I've highlighted a few here, but what we saw is that 2 things. One is the best forecaster changed over time. That was both because we went into different weather regimes, but also because some vendors were going in and they were making adjustments to their models over time and making improvements. And we've heard from some vendors, they're like, wow, we actually got to see this result. It wasn't, we gave some forecast and we never hear again. It's like, I could see this and make updates. The other part here is just, you can see for most folks, they're kind of following trends of like days that were tougher to forecast, the error went up for everyone. Days that were a little bit easier went down. And so that was very interesting from this, and kind of seeing like, where are we with the state of the art with forecasting? What can you get today and actually start using, with all the caveats that this was only in one region, the US. It was 9 vendors, but there are more vendors and, a bunch of additional things. How am I doing on time, by the way? Okay, cool. Another item here, which is sort of my interpretation of the results, is that when we look at the sort of best forecasts, we did see some things that when we're talking to the utility, we weren't sure if that's actually what you want in a best forecast. So this is a little bit of a cherry-picked example, but we saw here is that on this day, the forecast that had the best score was actually not even trying to predict those ramps. So this was an hour ahead, 5-minute resolution forecast. They were just kind of, they were making an effort, but we weren't seeing that huge oscillation, which brings up the question of, is that what you want? Because what if now, do you want a forecast that's just flipping up and down constantly? Maybe, maybe not. But it brings up an important point about what do we want of the forecast, and then having that information flow back to vendors and developers to say, this is what we really need. And if they're using AI models, they're using physics, whatever it is, but informing that, I think, is an important role of things like these meetings. I'll mention a couple of quick things about another competition. This was done in partnership with DOE. This was the Net Load Forecasting Prize. All the winners were announced back in September, but this was probabilistic forecasting, doing day-ahead net load, and at a substation level. And what was really great about this was we were able to get 4 utilities to partner with us and actually give us real data from their substation, anonymized and some other stuff. But this was really great, and we got 70 teams signed up. These were mostly not like commercial vendors. They were mostly like startups or maybe some universities or maybe someone that works in a related space, but now they're doing this. But we, again, used the arbiter, did this evaluation, some very interesting results. One I'll just mention here as a quick example is when we talk about probabilistic forecasts, so the color range is a probabilistic forecast, the black solid line is the actual, and then the red line, here I'm just putting the P50 as like a proxy for deterministic. But one thing we saw here is, lots of examples where you would see some event like a cloud pass by, and so the behind the meter sold goes away and your net load ramps up really quickly on the substation. But that probabilistic range actually still captured that. Now there's a question of like, what do you actually do with that? But it's an interesting one to point out of like, hey, this is sort of showing that, sure, you think this is where it's going to be, but there's high uncertainty in this day. And so having the probabilistic nature there maybe helps you to hedge for these sort of events and be prepared. So where do we go from here? Last thing, I think, and this is something that my team at EPRI has been talking a bit more about, is we have to think beyond just how the forecasts are created, but also how they're used, and think about what are the changes and improvements we need to do that are going to have the biggest impact. So I think we need to have more of this holistic kind of feedback loop to say, what changes do we need to focus on? Is it average error? Is it during extreme events? Is it during the morning periods where you don't know what the clouds are doing if you don't have satellite imagery, and that difference is going to make a big impact operationally. So I think just reducing the average error, even with these AI models, it's not enough. We should be thinking a little bit more about this. And the last thing I'll end on is a little bit of a plug, but EPRI has a load forecasting initiative that I'll probably be harping on a little bit this week. But anyways, we're doing a lot of work in this area. We're coordinating with ESIG on some items. A lot of these shared challenges we're trying to address and then to work with folks. So there's a QR code. I know the slides will be shared from this. You can also talk to me, but we're doing a couple of different things here to try to share knowledge and also tackle some high priority items. So as a little teaser, probably in the next couple of months, we're going to have something about data centers and kind of what people are doing today. On the short-term side, we're doing some stuff on extreme weather. And again, trying to get things out that are practical and at least get us moving forward. And of course, working with partners like utilities, vendors, et cetera. But yeah, with that, all set.